Thank you.
Our third speaker for this session will be Serge from Criekingen, and he'll be talking to us about some new course corrections for additive Schwarz.
Okay, thanks for the introduction. Thank you to the organizers. So I'm Serge from Criekingen. I'm coming from France. I'm working at Idris, which is the supercomputing center of the CNRS, and we are located in Orsay, south of Paris. And this is joint work with Martin and Gander from the University of Geneva. So the outline of my talk is this one. So after the introduction, I'll talk about coarse corrections, so coarse grid corrections, optimized interface conditions with Dubois to obtain the so-called ORAS2 method, and then I will present you some weak scalability results before concluding. So, as introduction, I want to say that the Additive Schwarz Methods, or ASM, are domain decomposition methods implemented in PETSc's PCASM tool. And the default PCASM is the Restricted Additive Schwarz method with an overlap of 1. So using PETSc tools, what we are going to do here is add 2 improvements to this method. First, a new course correction that will lead to a 2-level method that we call the RAS2 method. And then optimized transmission condition at interfaces, which will lead us to the so-called ORAS method. And combining both will lead us to what we will call the ORAS2 method. So mathematical setting, of course, we are solving Ax equal b on a domain called omega, split into subdomains omega j that can be overlapping. And so we introduce restriction operators to subdomains omega j to obtain local matrices on those subdomains, like this. And the additive Schwarz method is as follows. So we take the residual, we restrict it to the local domain, we solve on the local domain, and then we extend to the transpose of the restriction matrix is the extension matrix. We extend this, and we add that local correction to the whole thing. Now, to obtain the RAS method, we have to introduce a non-overlapping set of subdomains that we'll call omega tilde j, that also maps all omega. And so the difference between the RAS method, the additive Schwarz, and the restricted additive Schwarz method is just the tilde here. So the extension part must be done with this non-overlapping subdomain decomposition. And well, to get why RAS is better than RAS is not obvious. It was found accidentally by Kai and Sarkis in 1999. And I lead also you to that paper by F.U. and Gander from 2003. To explain why RAS actually works, I would say, better than the AS method. So, course correction. So I'm not the first one at this conference to talk about course correction. Here I'll have a very intuitive approach. So why do we need course correction? So basically, what are we doing here? Domain decomposition we solve in each subdomain, and at each iteration we take the value of the neighboring subdomain to improve our local solution, which means basically that at each iteration, information goes from one subdomain to the neighboring subdomain, which means that if you want information to go, for instance, from that subdomain there up to there, you will need at least that many iterations. So you can see directly that this is not scalable. If you increase the number of subdomains, you will need to do something, because if you increase the number of subdomains, the number of jumps will grow, and you will need something to have the information go faster throughout the whole domain, and that's why course correction is introduced. So the mathematical setting here is we introduce this time a restriction operator to a coarse space, which I call RC. We obtain coarse matrices, which I call AC, and the RAS2 method, the first half is just the same as the RAS method. And then we add a course correction just like this. So we take the residual and do the same thing as here, but with the course correction. How to do that in PETSc? Well, there was a tool for that. It's called PC Composite. So I compose the PCASM with a PC shell, and the course correction is implemented in the PC shell tool. So I want to illustrate that numerically. Very simple example in 1D, so just Laplace in 1D with boundary condition 0 on the left and 1 on the right. And I will just plot the first few iterations of the RAS2 method, that is PCASM alone or with PC composite, using a domain decomposition into 2 or 16 subdomains. So here, locally, I use direct methods, so preconditioner and PCLU, and Richardson method globally, so no Krylov acceleration, and the number of grid points is 80. So here, what you get with 2 subdomains, so the solution here is just a slope, so we go slowly to that solution, to iteration 1, 2, 3, and 4. So with 16 subdomains, as I explained before, it's going to be slower because information must transit from one side to the other side. So after 4 iterations, you are just at this point, so you are further away than with 2 subdomains. So we introduce a coarse correction. So now, how do you pick the coarse grid? The natural way to you think about, well, I'm going to take the midpoint of each subdomain, just like this. And what we call new here is to take the fine point mesh on the left and right side of the subdomain interfaces, so the squared ones here. So that was introduced by Gander and Dubois in the 2 references I give here. So I give the full references at the end of my talk. So that was give if I do the composition with the midpoints. So this at iteration 4, we are here at something which looks very good. At least visually, it's nearly the exact solution with 16 subdomains, so it works. But with the new coarse correction, it works even better because we have the exact solution at iteration 1. So what's the magic here? The magic here is actually that the new coarse basis functions that we introduce are actually harmonic, so they solve the Laplace equation within each subdomains. Which means that if instead of just the Laplace thing, I had taken the Helmholtz one with eta, non-zero eta here, I would not have had convergence at iteration 1, but still it would have been a very good result. So that was for 1D. Now in 2D, the equivalent is this for the midpoints. I don't think I have to say more about this. And the new coarse correction here is to take the coarse grid points, 4 coarse grid points around the cross points of the domain decomposition that we introduced. So in that paper, like Gander from 2014, there was a comparison between different choices of coarse grid points. So that was the coarse correction. So now the second improvement is the optimized interface conditions. So what is the idea here? So far, let's say at the interfaces between subdomains, we have been exchanging the values between one subdomain and the neighboring subdomains. And so the idea here is, on top of just the values, we can also exchange derivatives of these values and combine both, and we then obtain a so-called Robin interface condition. That's what we are going to do here. So again, I take the RAS method, just the same as before, but this time I will replace the local matrices AJ with head J matrices, where these are discretized local problem with the Robin boundaries of interface conditions. That looks like this, so a combination of Neumann and Dirichlet boundary condition with a factor P that can be optimized. To yield, so this yields the ORAS method, so the difference here is just that hat here in the local matrix. So of course the choice of a hat of the local matrices with Robin condition is not unique. It depends on the problem, on the discretization. And what is good is that the parameter P can be optimized, so which explains why we talk here about a RAS method, so optimized RAS method. The reference for this is St-Cyr from 2007. So for my rescalability test, later I will do the 2D Laplace problem on the unit square with 5 points finite difference. So as in the reference, I mention here, if we take a first order discretization of the normal derivative, we have only to modify the diagonal elements on the local matrices to obtain the A hat J matrices. And we have also formulas for what the optimal value of P is, so they are given here, where small h is the fine mesh size, capital H is the coarse grid parameter, and the overlap must be positive. So one has to be careful here, because when the overlap is 1 in the PETSc sense, it means that the algebraic overlap is actually 2, and the physical overlap is still something else. But here, well, the overlap I used in the results I will show you. So the overlap values are the ones in the PETSc sense. And so, what is the tool to do this in PETSc? It's the PC set modify submatrices tool, which enables to build the corrected local matrices. Okay, so now I combine coarse correction and optimized interface correction to obtain the RAS2 method. So that was our RAS2 method, and I write exactly the same, except that I had a little hat here on the local matrices. So that's how it looks in PETSc. So it's a PC composite, multiplicative composition of PCASM with PC Szyld. This is just to define further the submatrices, so the optimized RAS correction, so for the Robin interface condition. And this is how you define the code space through the PC Szyld function. Okay, weak scalability results. So again, I repeat that I'm using the Laplace problem on a unit square with 5-point finite difference. I'm doing mixed scaling experiments, and I will increase the number of subdomains, so which is equal to the number of tasks and CPU cores. So that will be J in my slides. And I keep the constant of the fine mesh size on the coarse grid size constant, so that those with two possible values. So the machine I used at my institute, so the first one is ADA, which is I would say, a regular cluster classical. The second machine is a Turing machine, which is an IBM Blue Gene Q, which is pretty old, but still in use till next year. It will be replaced next year. And I also had access to another machine called Occigen at the CNES, which is another computing center we have in France. And all those machines are funded by GenC. So here are my results. So this slide is just to show the importance of the two-level method. So you see that the two-level RAS are just increasing like way too rapidly here to even be seen on the map, on the plot, and for ORAS it's better, but it's still, so these are the ORAS without two-level, and this is with a second level, so that works much better. So the second level here really clearly, as expected, gives the scalability. So now I merge the two graphs, but keep only the two-level results. So here are the RAS2 results, and we see that the ORAS clearly improves on the RAS2 method, even though like overlap 1 and 2 or 2 doesn't, to add one level of overlap doesn't help much, but going from RAS2 to ORAS2 clearly helps. So that's for a number of iterations. So now I'm going to time. So these are the timings on ADA. So it's just in terms of RAS and ORAS is the same. So RAS is here, here, and here, and ORAS, they are all both here. You can distinguish among them. And so I found it interesting to just apply the hyper multi-grid preconditioner to the same problem. So I insist this is default hyper. It's just minus PC type hyper at runtime. It's nothing more. So I would say hyper specialists can probably do better. But this is just the default option of hyper, and that's the timing I obtained. That's up to 1,000 cores. And so I would say that our methods are competitive. And but the timing here is just 5 seconds. It's not much, so I took a bigger problem going from 0.04 to 0.02. So the times are a bit bigger. And so here again, ORAS, so RAS is here, ORAS is here, ORAS2 is here, and hyper is here. So again, our results are competitive, I would say, with the default hyper results. So this is up to 1,000 cores, so I wanted to go higher. And so I used the Occigen machine. So I could go up to 16,000 cores. And so the results are quite the same. So the ORAS2 and the hyper are like all together here in terms of timing. I also did the same thing on Turing machine, where I could also use 16,000 cores. Here there is a big difference, well, like a nearly factor of 2 between hyper and ORAS2. Actually, it's normal to go slower on Turing than on Occigen, but that's because like Turing is a very specific blue gene queue architecture. But let's say like hyper suffers less than us from going from one machine to the other, and that's probably because the hyper library is very well optimized and has been very well optimized over the years. My last plot will be about the memory footprint on the Occigen machine up to 16,000 cores. And here, so this is for the RAS. You can distinguish between the different overlaps. So this is the RAS, this is the ORAS, and this is hyper. So clearly hyper has a smaller memory footprint. Okay, conclusion and an outlook. So we've seen that the combination of the two-level method with the new coarse correction plus optimized interface condition yields substantial improvement on the standard RAS. On the 2D Laplace problem, the ORAS2 has been shown to be competitive with the default, I insist, hyper up to 16,000 cores despite a larger memory footprint. And all this is relatively easy to implement with existing PETSc tools, so PC Composite for the two-level and PC set modified submatrices for the optimized interface condition. Of course, this is just, I would say, this is only the Laplace problem. So outlook to go further would look at real-life problems and go beyond the Laplace problem. To talk about, to do something for the 3D case, and maybe on a longer term, to have also optimized Schwarz for the non-overlapping case, because what I showed you was only for the overlapping case. But for that, I will, I think, need to use augmented systems, so you will have to duplicate interface values somehow, so that's not going to be, I think, immediate. Okay, so acknowledgements. I want to thank Olivier Dubois from John Harbert College in Quebec, Canada, who provided me with the code he did some time ago, and that helped me a lot. And I also want to thank CNRS Idris, my colleague at CNRS Idris, so my fellow team member. Okay, and as promised, this is the full reference list. Thank you very much, and thank you for your attention.
So what happens to the timings if you use the RAS as a preconditioner instead of as a solver?
It's about the same. I did the same thing with GMRAS on top of, instead of Richardson, and I got similar results, I would say.
So how does, is there anything about your framework that requires that the original system be symmetric?
No.
That would be interesting to see what happens with some asymmetric problems too.
Okay.
Because
You think?
in the last 5 years I've been solving basically non-symmetric, completely crazy systems, and Additive Schwarz is the only reasonable thing that they have at hand to throw at it. So any improvement there, completely new phase field or crazy high order PDEs,
Okay.
trying something non-symmetric and verifying how things are working in that case will be quite interesting.
You would have an example of? We can talk later.
We can say, I mean, can clear equations which are discretizing
Okay.
primal form, but for not in high order precision, or let's say advection diffusion,
Okay.
or not, anything that is non-symmetric that moves away from a swan or a class.
Yeah. Sure.
Very good. I think lunch is sponsored, so let us thank all of our speakers.
Thank you.